Okay, so the last talk of the session is on malicious secure structure-aware privacy intersection from Gayatri Kandala, Mike Bozulek, and Jasper Chen. And Gayatri is one. Is this
Yeah, it's Gayatri. Yeah, so good afternoon, everyone. Thanks for being here. I'm really excited to be talking about this new result in private set intersection. This is based on joint work with my PhD advisor, Mike Roselig and Jaspal Singh. So private set intersection is a special case of secure two-party computation. Here, Alice and Bob each have a private set of elements. And Alice wants to learn the intersection of their sets. That is, she learns that the letters R, I, T, and E are common between both their sets. Bob is suspicious of Alice and wants to be assured that Alice only learns the intersection, and everything else about his private input is hidden from her. On the other side, Alice is even more suspicious of Bob and wants to be assured that Bob learns nothing about her private input during the course of the protocol. PSI finds many useful applications in practice. And in the last decade, many interesting techniques have been evolved to design efficient and scalable schemes for PSI. Last year, we studied a new variant of this problem that we call structure-aware private set intersection. So here, Alice's input has some publicly known structure. For example, both Alice and Bob might be aware that Alice's input is an interval of points. Or maybe it's a geometric ball or the union of geometric balls defined within some metric space. So let's look at an example. Suppose Alice's structure is this square, then here her private input is the square that's centered at some point that she chooses. On the other side, you have Bob, who has a set of unstructured points within the same metric space. And the goal is for Alice to learn the intersection of these sets. That is, she wants to learn the identity of all the points that lie within her chosen structure. And the privacy guarantee is that nothing about the points that lie outside the special structure must be revealed to her. On the other side, Bob is supposed to learn nothing new during the course of the protocol. So this is a cool formulation. And where can something like this be useful? Well, one of my favorite applications is this privacy-preserving ride-hailing service. So imagine that you're looking for a ride, but you're also privacy conscious, so you don't want to reveal your exact GPS locations to the cab service or the drivers in the area. So the goal is for you to be mapped with the closest available driver, maybe someone who's within delta distance of your set. So one way to model this search space is as a union of delta radius balls. And it is public information that one of both parties' sets has this structure of being a union of delta radius balls. So now this seems like a suitable application where we could have structure-aware PSI. And if we did have such a protocol, then every person who's looking for a ride can get mapped to the nearest available driver while being assured that their location privacy is maintained. So let's see how we can solve this problem. Well, one naive approach is to just ignore the fact that Alice's input is structured. Just treat it like an unstructured set. So what Alice can do is just enumerate all the points within her structure. Then you can just pick the latest and greatest available communication and really fast PSI protocol that's available. And then Alice and Bob can run the protocol so that Alice learns the right result. And sure, this works. But the issue is that these standard PSI protocols are designed in such a way that the communication cost and the computation scales with the cardinality of both the parties' input sets. So let's see what this means with an example. So suppose Alice's input is this union of orange colored balls, then maybe her, so if you were to use standard PSI, then the communication will scale with the total volume of balls that lie within Alice's chosen input. But qualitatively, what we're asking for is that can Alice's communication scale with a more succinct description size of her input set, given that this is public information? So instead, what if a communication scales with the number of balls within her input set? Can this be done? Well, last year, we answered this question in the affirmative, and we presented a generic paradigm to get structure-aware PSI in the semi-honest model. So if you have a structured input, and you can compactly represent the structured input by a Boolean function secret sharing scheme, where the share size is sigma, then now Alice's communication will scale with this share size instead of the cardinality of her input set. So let's recall what a Boolean function secret sharing scheme is. So if you have a set A, then you can secret share it so that you learn two shares, the blue share and the pink share. And each of these shares are going to look pseudo-random to you. That's the privacy guarantee. And given these shares, you can evaluate these shares on any point and combine the result. And this result will indicate membership. So if the result is 0, it tells you that your chosen point lies within the special set A, and otherwise, if the result is 1, then it's outside the special set A. So this was our previous result, and in this work, we asked the question, can we extend this paradigm to the malicious setting, where either Alice or Bob could be active adversaries that deviate from the steps of the protocol? So we start by revisiting the semi-honest construction, and we reason about why it's not immediately malicious secure, and then we look at how we can fix it. So this is the semi-honest construction. So Alice has a structured set A, and she has access to this function secret sharing scheme. So she secret shares her set not once, but kappa times, where kappa is the security parameter, which is usually 128 bits. Now, Bob has kappa choice bits. So he gets to decide whether he wants to learn the blue share or the pink share. And then Alice and Bob run an oblivious transfer protocol so that Bob learns the right FSS share that he's looking for. By the oblivious transfer, it's guaranteed that Alice is oblivious to these choice bits. So she has no idea which FSS shares Bob picked. And this is all the interaction you really need. After this point, Bob defines this special function f. And to evaluate this function f, he evaluates all his FSS shares on any given point. Then he concatenates the result and feeds it into a random oracle. And the result of the random oracle is this evaluation of this function f on a point x. The crucial thing to observe here is the way this function f is defined depends on Bob's choice bits. Okay, it inherently contains all the information about Bob's choice bits. Now, because Bob made these choices, he can compute this function f on any point that he chooses. And specifically, he computes it on every point that lies within his unstructured set, and he sends it across to Alice. Now, from Alice's perspective, Alice can compute this function f only when her point lies within this structure set. And this comes from the property of the FSS scheme. Because whenever a point is within the structure, it doesn't matter whether you're evaluating on the blue share or the pink share. It gives you the same result. But whenever a point lies outside her chosen set, then this f function looks random to her. And that's all you need to realize PSI. Because now Alice can make these local comparisons to realize and identify all the points that lie within her set. And this is the semi-honest construction. So all you really need is an efficient scheme to do function secret sharing for any structure that you like, and you can realize semi-honest PSI. Now let's reason about why it's not malicious secure. First, let's look at the easy case where Bob is corrupt. Notice that all Bob does in the protocol is indicate choice bits, and these choice bits are independent of his input. So there's not that much he can do. And one thing is you just replace these semi-honest OTs with malicious OTs. So the far more damaging situation is when Alice is maliciously corrupt. Well, one thing she could do is that she could secret share inconsistent inputs across these kappa shares. Another thing is that she could just feed in junk values to this FSS shares. They need not even correspond to the structure that she claims to have. Okay. So essentially, to realize this PSI protocol in a malicious setting, we've reduced the problem to this consistency of bFSS shares problem. So somehow we need to enforce that Alice encodes the same input across all these shares, and Bob wants to have like a guarantee of this. So let's fix this. How can Bob detect this kind of misbehavior? Well, we'll use a cut and choose style check. So here, Bob gets to pick some subset of indices, and Alice secret shares her set T times, where T is a cut and choose parameter. Now they do the usual thing with the oblivious transfer, and Bob learns his shares. Now, Bob reveals the indices that he would like to check, and Alice promptly responds by presenting both FSS shares at each of these indices. Now, Bob can check two things. One, he can look at both these FSS shares and he can verify that they're valid FSS shares with the same structure that Alice promises to have. The second thing he also wants is that Alice should encode the same set across all instances. So he could extract the underlying set that each pair of FSS shares encodes, and he can check for equality at all indices that he checks. And the cut and choose parameters will be picked in such a way that if these checks pass, then amongst all the unopened indices, at least kappa of them are valid FSS shares. And that's enough to protect Bob's privacy in the protocol. So this is nice, but there's one major issue here. Well, that is that Bob can reconstruct Alice's entire input in the clear. And if he looks at any pair of FSS shares at any given index, then if he extracts the underlying set, then he can completely learn Alice's input. And this leads us to two questions. How can Bob verify that a single FSS share is valid without learning anything about Alice's input? And second, we look at how can Bob check that these different FSS shares all encode the same input. To solve this first issue, we introduce a new variant of function secret sharing that we call Derandomizable function secret sharing with the following properties. Before that, I'd like to acknowledge some prior work where Boyle, Gilboa, and Ishai have introduced FSS schemes with some notion of derandomizability in a different context. But their constructions are limited to the set of offset families. Our definition extends to a larger family of sets. So suppose, let's understand this definition via an example. So suppose your structured input is a square and you have this specific input A, which is a square centered at point C1. Now, your secret sharing scheme is going to be randomized. So you're going to learn secret shares of this new pink square, which is a random object that's centered at a different point C2. Along with this, you're also going to have this notion of an offset or a correction value. Just think of this as the translation vector between this random object back to your true input. Okay, so here it could just be the distance between the two centers of these squares. And then you can do evaluation. So we have this notion of derandomizable evaluation, where now you can evaluate on these random shares corresponding to this pink square. And given this additional term of an offset, it still tells you membership of your true input, which is your black square. So said differently, it means that if you have an FSS share of a random object and this right offset value, then it's equivalent to having an FSS share of this true input A. And the privacy guarantees that just looking at one of these FSS shares and the offset, it looks pseudo-random and it protects the privacy of this true input. So now let's see how this derandomizable FSS can help Bob check for valid encodings. So here, Alice secret shares calls this derandomizable FSS t times, and she secret shares random objects which have the same structure as Alice's input. She also sends a commitment to each of these random objects, and she sends a commitment to the right correction values. And then you do the OT, and Bob has some indices that now he would like to check. And once he learns both FSS shares, given at any given index, he can verify if these shares are valid and have the same structure as Alice promised. And he can also verify whether it's the same random object that Alice committed to. And again, by the cut and choose parameters, you have Bob's privacy. And now Alice reveals the correction values for all the remaining indices. And then, like I mentioned earlier, given a single random share of a random object with the right offset is like evaluating on an FSS share of your true input. And then you can do the usual thing. So this almost works, but there's one more issue. How can you be assured that Alice does generate these offsets correctly? So zooming into what this means, what if Alice sends offsets that correspond to inconsistent inputs that de-randomize back to different inputs? So to maintain this consistency, we use homomorphic commitments. So now we require Alice instead to homomorphically commit to these offsets and to these random objects. And now Bob is able to verify. So he simply adds these commitments and verifies if they all correspond to the same set. And this gives you like strong enough guarantees that at least kappa of the unopened FSS shares are valid and correct. So that fixes all the issues that we had. And in a snapshot, this is the protocol to achieve malicious secure structure-aware PSI. And the real contribution of this work is that now you have this framework. And for any new application that comes up, or for any interesting structure that you can think of, all you have to do is design efficient schemes for de-randomizable FSS, and then you can instantiate the protocol. So I'll summarize our contributions. We also formalize this notion of de-randomizable FSS and present constructions for the point function, for the interval function, and also for the d-dimensional interval. We also present a construction for the union of balls within this L infinity metric norm. And for this, we use a special technique called a spatial hashing technique. And interestingly, this construction also improves the previous semi-honest construction for the union of balls FSS in this L infinity norm. And more generally, we're able to show that if you have a de-randomizable FSS, it's also sufficient to instantiate semi-honest PSI. So now all you have to do is design efficient schemes for de-randomizable FSS with good, with succinct share size to get good communication. And finally, I'll switch to presenting some open questions. So far, I only talked about Alice's communication, and theoretically, this is very interesting. But to realize PSI, we also have to consider the computation. And in this construction, Alice's computation still scales with the entire cardinality of her input because she needs to compute this FSS value over her entire input to recognize Bob's function evaluations. So it's still open whether can we have the computation also scale with Alice's description size, both in the semi-honest and malicious setting. Second, the way we have designed the protocol, the person with the structured input learns the result of the PSI. But it might be interesting in some applications to have the person with the unstructured input also learn the result of the PSI. So it's unclear how you could do that. And also you can look at what if both parties have structured inputs and if there are cool applications where you might need something like that. And finally, just designing better FSS schemes for different metric spaces. I think we'll just scratch the surface. There's lots to be done.
So much. The questions, please. So in the meantime, I want to ask you, what is the overhead compared to like traditional PSI, traditional malicious PSI?
So I think it's about like, so you could like compare with malicious PSI, but we're like actually solving like a completely different problems here, right? Like with structured input. So we do have the overhead with the semi-honest construction. So it was about like, if you had Alice's set with about 10 million points, and then Bob's set with about 1 million points, then the overhead in communication was about 10 times with the semi-honest. And then for the semi-honest versus malicious construction for these same parameters, we have about 6 times overhead. Yeah.
Does this work for any input domain? What do you mean? Like if the inputs are from
Yeah, it could. Yes, it could. Yeah, it could, as long as you have like a well-defined notion of a metric space on it, so that you can define a metric space.
I was label PSI or simple PSI.
Sorry?
Yeah. So I just wonder if the protocol could be extended to the cases where we have
Label PSI.
or simple PSI.
So can you define label PSI?
Yeah, let's say your offset each point associated with some specific labels or values, and Alice only knows the value associated to the intersection.
I mean, that's an interesting question. I guess you'll have to like group your inputs also, right? So you want Alice to only learn the labels, but not the true input.
Yes.
Yeah, so I haven't thought about that, but yeah, it can. Thank you.
Thank you. Let's thank the speaker again. So to reward you that you chose this session, you can go and get more free swag and have some extras. So you can go to the registration desk and get some extra jackets. So go now. I don't know how much is left, but we have